All right, let's continue by finding the domain of each function. At this point, you've seen the definition of domain. You've looked at ordered pairs to determine the domain. You probably even looked at a graph to determine the domain. Those are all more intuitive because you have something to look at. It's easier. What happens when you have just a flat out analytical, an equation, and you're asked to determine what is the domain if all I have is this equation? That's a little bit more difficult. So we're going to take some time and look at a few examples about how do we find the domain of each function. Number 7. Okay, just to get some language out there too, number 7 is what we call a polynomial function. And really the definition of a polynomial function is that if you have any exponents, those exponents can only be whole numbers. For example, 2. 2 is a whole number. What if 5x to the negative 2 is present? Well, negative 2 is not a whole number, that's an integer. So this is a polynomial function for 2 reasons. 1, any exponent is a whole number. And of course, we have that understood 1 right here. Okay. And that the coefficients on any term, so this polynomial has 3 terms. Terms are what you add or subtract. So when I look at this term right here, the coefficient is a real number. 5 is a real number. When I look at this term, the second of the 3 terms, 4 is a real number. And the constant also has to be a real number. No imaginaries, no i's. And you might remember i's from your study in Algebra 2. Anyway, polynomials are the easiest functions to find domains of because these functions are well behaved. There's no breaks in the graph. They continue from far left to far right of your screen. So this is actually a parabola that opens up. Where is it? I don't care. But I know there's nothing weird going on. So the domain of any polynomial function, whether it's linear, a constant flat straight line, as long as it's not vertical, okay, a vertical line, a quadratic, a cubic, the domain is all real numbers. All right, these remaining 5 problems that you see, they're rational functions. They're not polynomial functions. They're rational functions. They may have breaks in them, like asymptotes, vertical asymptotes, or even like a point that's missing. Okay, they're kind of interesting. So these are rational functions. And when you think about the first part of the word rational, I think about ratio, fraction. Anyway, not all fractions produce like breaks in the graph. For example, what if on number 8 I would have changed it and put not in the denominator? What if I would have just had a number like 7? I mean, heck, it can be anything, but what if I just put 7 down here? Okay, well, actually, I could rewrite this. I'm going to slide the numerator off. I kind of hate using non-technical words, but if I rewrote this, I can actually put the 1/7 in front of 9x minus 4. I could distribute the 1/7 in, and actually I get a polynomial. So don't think that every time you see a fraction bar that you have a rational function. It really just depends upon what's in the denominator. Is there a variable in the denominator? Because then the answer is yes, it's a rational function. If the denominator is just a number, well, I can slide the numerator off, distribute that number in, and I'm going to end up with a polynomial whose domain is all real numbers. So just kind of be careful in saying that anytime you see a fraction bar, that's going to be a rational function, because not always. It has to have a variable in the denominator. Okay, so number 8. In order for us to find the domain, I first of all see, oh my God, this is a fraction. Let me look at the denominator. Now, this is kind of sad to say, but the numerator, for this question about finding domain, if I have a rational function, I can disregard the numerator. The numerator has no connection to answering the domain question. It's the denominator. So when I look at this fraction and I think of any fraction, the only thing I never want to divide by, the only number that's illegal to divide by in math is 0. I do not ever want to divide by 0. It's a bad thing in math. So do I have a variable in the denominator? That's the first question. Yes, I do. So then I disregard the numerator, I focus my attention on the denominator, and I say, what can x not be? This might be a different way of what you've been taught and thinking, but I'm going to say the denominator, which is x, that's the entire denominator, cannot be 0. That's a restriction on the value for x. X can be any other number but 0. X cannot be 0, anything else is okay. So how do I write the domain in interval notation? Well, a number line might help you get there. So if x can't be 0, let me build a number line, put 0 here, put an open circle, which means exclusion, and then if I extend my arrows in either direction to the left or right off of x equals 0, I'm saying any of those x values are acceptable as replacements in down here. I don't care that there's an x up here. I could get a 0 in the numerator. Okay, you just can't divide by 0. The 0 can't be in the denominator. So how do I transition off this number line? Because I want my answer in interval notation. And I should have put that up here with the directions. Use interval notation. Well, the domain, I'm going to start from negative infinity. I'm going to work my way to 0. The parentheses mean you're going to exclude the 0. I don't know if you use a union or a comma. I'm going to put a comma, and then I'm going to pick up again from 0 going to positive infinity. Both are acceptable, whether you use a comma to separate these two sets of x values or you use a union. All right, look at number 9. Let's find the domain. Wait. Oh yeah, domain. I have a fraction. Do I have a variable in the denominator? Oh, I do. Take the entire denominator and say that that denominator cannot be 0. Think of it as an equal 0. Now let's solve for y. Divide by 3, divide by 3. 3's divide out, y cannot be, and that's still 0. So the answer is the same thing as number 8, so all real numbers except for 0. And we show that using interval notation exactly the way we showed it in the previous example. Number 10. Anytime, stop the video, you try it. Come back and check. If you're right, you're right. If you're wrong, who cares? Fix it. All right, let me find the domain of f of k. Okay, so the domain question means let me connect to the denominator. So k plus 3 cannot be 0. That entire denominator cannot be 0. How do I solve this for k? Subtract a 3 to the other side. So k cannot be negative 3. So number line, negative 3, excluded with an open circle. All other values for k will work. Okay, I think the way I do this is slightly different than some other teachers. It's just different, it's not wrong. Most teachers for the domain question would have you set the denominator equal to 0. Fine. Okay, but then you just have to know in your brain, well, that's the number I can't include in all real numbers. So that's the only thing I'm doing different is the does not equal. All right, what do you think about number 11? Well, I see 2 fractions, so it looks like it's 2 problems in one. Oh joy! So let's treat each fraction separately, finding the restrictions in the denominators of each of the 2 fractions. So let me just start with this fraction. So, oh, there's a variable. X cannot be 0. Finished with that one. Then I'm just going to come over here and say, comma. Okay, now let me focus on this fraction. X plus 2 cannot be 0. I can't divide by 0. So this whole entire expression can't be 0. A little bit of math here. Subtract the 2 to the other side, so x cannot equal negative 2. So notice that we have 2 x values that are restricted from all real numbers, but everything else works. So I'm going to draw a number line to help me organize my work to jump off of it to put my answer in interval notation. Make sure you order these correctly on a number line. Hello, negative 2 is smaller than 0. So negative 2 would be to the left of x equals 0. Both of these x values are excluded. They're restrictions. Makes you divide by 0. Bad thing. Okay, and then let's just fill in all the gaps. So it looks like we're going to have 3 sets of parentheses for each of these intervals. So I'm going to stop at -2, but then I'm going to restart at -2, and then end at the next restriction, x equals 0, and then start again. Oh, that's going to be infinity. Need to get an eraser. All right, try number 12. Did I ever look at any of the numerators of these rational functions? No, because for the domain question, I don't look at the numerator. I only look at the denominator. Are there times that I need to look at the numerator of a rational function? Yeah, that's usually if they ask you to find the zeros or the x-intercepts, but not this question. All right, how do I solve this? Well, please don't move over the -2x and divide out an x, because then you're dividing by x and x might be 0. That's a bad thing. So how do we tackle solving this here? Well, I can factor out the x. Remember, always check your work by distributing back in what you divided out. So if I distributed x back in, yes, I'm getting to x squared. Distribute x back in, I'm back up here. I mean, what harm is that? It takes you 2 seconds. Check your work. It might avoid some errors later. All right, so either x can't be 0 or x minus 2 can't be 0. And parentheses aren't necessary here. I need to get an eraser. So that's not there. Add a 2 to the other side on this equation, so x cannot be 2. So our two restricted x values from the domain are 0 and 2. What am I going to bump into first? X equals 0. And then I got this in-between spot here, 0 to 2. And then it looks like it goes from 2 to infinity. Good time for a brain break. Pause me, come back. Last objective, determine whether the equation represents y as a function of x. Do these equations, when graphed, produce a graph that would pass the vertical line test? You saw Mrs. Garcia talking about that. You had a visual of a graph. She had the toothpick. Problem with this is some of these you can't enter right into the calculator and then look at a graph, because the equations are not solved for y. Not all of them anyway. I see these two equations are solved for y. Let's start here, and then we'll tackle these other 4 where these equations are not solved for y and see what we can do. Okay, 15. Is this equation going to produce a function? A graph that passes the vertical line test? Well, when your equation is solved for y equals, I would say you're, probably going to have a function. But a graphical representation of this is a square root graph based on your parent function graphing, the square root graph with the shift left 3 off the origin. So if I moved over left 3 to x equals -3, that's what this graph looks like. You got a visual, or type that into y1, look at the graph. Does your graph pass the vertical line test? Yes, it does. All right, look at 17. Oh, sorry about that. Let me push that up a little bit more. Okay, based on your background with this type of function, this is an absolute value function. Y equals, I can enter this into a calculator, and the calculator is a function graphing calculator. So I'm going to go ahead and say yes to this. If I can get y by itself, and I just have something that looks like either one of these two, yes. So a visual for this would actually be, this is an absolute value function upside down. It might be shifted to the right. Let's see, when x is 0, y is 4. No. I think it looks, well, when x is 4, y is 0. You can put it in your calculator. It's an upside down absolute value graph. The point is, does this graph pass the toothpick test? I'm sorry, the vertical line test. Yes, it does. All right, let's tackle another easy one. Let's look at 16. Can I solve this equation for y? Yes, I can. And then let's take a look at that equation to see if we know anything about it, if we can produce a graph or we can put it in the calculator to get a visual. So I'm going to move the 2x to the other side. So 3y equals negative 2x plus 4. Then I'm going to divide by 3. You could divide the entire right side of the equation by 3, or you can put each of the terms under 3. However you want to do it. So this is going to be a graph of a straight line. This domain is all real numbers. Notice there's no variable down here. Remember what I said earlier. You could actually slide that numerator off, take the 1/3 and multiply it in to negative 2x plus 4. And when you multiply that in, it's still going to be a linear function. So yes, this is a function. All right, let's take a look at 13 and 14 grouped together. This is actually going to produce a circle. And I want you to think about a circle. Would a circle pass the vertical line test? Nope, it'd fail it. So our answer here is going to be no. But what's the math that supports that answer if you did not know that this was producing the graph of a circle, which is not a function? So for me, what I do is I begin to solve any equation that's not solved for y. These two were solved for y equals. This was an easy solve for y equals. I take 13 and I go ahead and I try and solve for y equals. So let me subtract the x squared to the other side. So y squared stays by itself on the left side of the equation equals negative x squared plus 4. All right, I have an even power here. I have a square. To undo the square power, I'm going to do the inverse operation of square rooting. So I'm going to write the problem down again because I don't want to write on this. I want to see what this was previous. So I'm going to bring in a square root here, an even root. 2 is an even number. I'm bringing in an even root for an inverse operation. With even roots, not odds, if this had been y cubed, I would not do what I'm about to do next. If this exponent was 5, 7, 9, any odd exponent, I would not do what I'm about to do next. But because 2 is an even number, and it could have been 4, 6, 8, or any other even number, when you bring in the inverse root, that even root, when I take out y, I have got to put absolute value around y. There are two solutions that can happen with even roots. And I want you to just think about it. 2 times 2 is 4. 2 is positive. What about negative 2 times negative 2? That's also 4. So when you have an even exponent, there's a possibility of having two solutions. Now, when you have an odd exponent, okay, my answer isn't going to be the same number if I multiply by evens or odds. What I mean is this. What's 2 times 2 times 2? Well, that's 8. But what's negative 2 times negative 2 times negative 2? That's negative 8. So for odd powers, you're only going to have one solution depending upon what you're multiplying by. For even powers, you're going to have either a 2 or a negative 2, okay, or two different possible answers. So my point is this. When you bring in an even root, whether it's a square root, fourth root, sixth root, you need to bring out y with the absolute value around it. So over here, can I simplify? No, I can only simplify radicals when I'm multiplying. So I still just bring this down. Okay, now here's some more math here. How do I get rid of the absolute value bar? Well, absolute value means a number's distance from 0. So for example, let's come over here. We're just tying in a lot of math. What if you were asked to find the absolute value of y equals 2? What could the value for y be in between the absolute value bars? And when you find the absolute value, you still get 2. Well, I hope you're thinking, well, y could either be 2 or y could be negative 2. That's right. So how do we, when we remove these absolute value bars, how do we show that we're going to have two solutions, either 2 or negative 2? Well, we make an adjustment over here in front of 2 to plus minus. So the work and the step to go from here to here, when you remove absolute value around the y, you come to the right side of the equation and you make the adjustment to plus minus. So let's import that back over here. So I'm right here at this step. I want to take the y out from the absolute value, but in front of this square root, I have got to put a plus and a minus. So I have two solutions. I've got y equals the negative square root, and I have y equals the positive square root. Oh, I think that's a negative, pardon me, and a plus 4. So sorry. Negative x squared, yeah, plus 4, negative x squared plus 4. So when we think about this, try a value for x, like let x be 0. If x is 0, you're going to get the square root of 4, which is 2, but then we have to make this negative 2. Let x be 0 here. When you add it to 4, you get 4, square root of 4 is 2. So this solution, when I plug in 0 for x, would give me negative 2. When I plug in 0 here, it gives me positive 2. When I plug in the same input value, x equals 0, I get two different output values. No, not a function. Because if you were to graph 0, 2, and 0, negative 2, notice how those 2 points, ordered pairs, stack up vertically and fail the vertical line test. So can we look at the equation and go, you know what, that's an even power? Is that a shortcut? Sure. Look at y, find y. If you were trying to solve this equation for y, you have an even power, which means you're going to end up with two solutions. Well, that means you're going to have two outputs for the same input. That would not be a function. So skip your eyes over to 14. Okay, what do you predict the answer is to this question? Is y a function of x? No. Well, what if y was to the third power? It's not because it's a power other than 1. It's because y has an even power. What if the problem had been, so this answer is no. What if this had been y cubed equals x squared minus 2? And I want to look at these side by side. A lot of math here, but good math, upper level math. The answer to this question is no, but we're going to kind of explore and extend this math. All right, if I were to solve for y, let me write the problem down again. Let me bring in the square root, an even root. Oh, when I take the y out, oh, always go back and double check because I brought in a root that was even. I'm not bringing in a power, I'm bringing in a root. Okay, I'm going to put absolute value around it, and this just comes down. Now, next step, I got to get y by itself. I can't put this into the calculator this way. To get y by itself mathematically, I know that I'm going to have two solutions, the positive and the negative. Well, right here, if your input value is 4 or 6, you're going to either get a positive or a negative answer. So this is what causes us to fail for this function to be, or for this equation to be a function, this even power. Now, I want you to contrast that over here, okay? What if I wanted to solve for y? Well, to solve for y, I'm going to bring in a cube root. So let me rewrite the problem. Let's bring in an odd root. So you got to put a 3 here and a 3 here. All right, now an odd root undoes an odd power. Well, the same. Okay, so I'm going to bring out the y. Oh, wait, okay. Do I have to put absolute value around this? No, because there's only going to be one solution, either a positive or a negative answer. Okay, for even powers, you're going to have two solutions that give you the same positive answer. So no absolute value. So then just bring down the right-hand side of the equation. Notice you don't have a plus minus in front to generate two different answers.